Hello students, we are going to look at halogen derivatives class exercise 2. This particular class exercise allows you to have a glimpse of one type of question that will often come out for exam, that is synthesis. I think I would have gone through some of these different types of questions during the tutorials, but I thought I'll just do a summary here. So the first type you're going to expect is synthesis. So in a synthesis kind of question, you are given the starting material as well as a product. So you are supposed to plan a synthesis going from the starting material leading to the product. They will normally tell you how many steps you need. In general, for H2, you do not need more than 4 or 5 steps. If they do limit you, then if you require more than 4 to 5 steps, that means something has gone wrong in the way you plan your synthesis. Yeah, and because of the limits in the number of marks we can award for this kind of question, usually we do not require the students to do extensive thinking when it comes to synthesis kind of question. Yeah, so for synthesis, you should also be familiar with reagents and conditions. Yeah, because when you are planning out your synthesis, right, you are required to highlight what are the reagents and conditions that allows you to transform your starting material to the intermediate products and then eventually to the final products. The next kind of question is also quite popular with students and quite popular for exams. That is mechanisms. Okay, so for mechanism, you can sort of divide them into two kind of categories. One is those in the learning objective, I call it LOs. What are those in the learning objectives? You expect, say, free radical substitution, which you have learned in alkane, electrophilic addition, which you have learned in alkenes, electrophilic substitution, which you have learned in arenes. Yeah, that was the topic you have done after promos last year. And then this current topic, nucleophilic substitution. And in nucleophilic substitution, you need to be familiar with SN1 and SN2. Okay, first order and second order nucleophilic substitution respectively. And then finally, the next topic, or rather 2 topics later, you're going to learn nucleophilic addition, which has got to do with carbonyl compounds. Yeah, so those are in the LOs. And then you are also going to expect novel kind of mechanism that will be tested, but they will usually be heavily guided in exams. We call them novel mechanisms. Okay, so do look out for the clues so that you are able to solve them easily. And then the third kind of question we're going to get is distinguishing tests. Okay, so you're going to see that in the final bit of this particular exercise. So that is at 2C. Sorry, not 2C, 2D, where you're supposed to use appropriate chemical tests, write down observation to confirm the identity of R as a bromoalkane. Yeah, so distinguishing test is usually the easiest among students because you can religiously study for it, and they often come out in practicals as well. So distinguishing test. The fourth kind of questions that you're going to expect will be the hardest for students in most cases. An example will be like 2A. Okay, it's what we call structural elucidation. So normally we start off by telling you that, okay, this particular compound has a molecular formula of blah blah, and then after that you subject it to this particular reagent, and then you're going to get another compound B maybe, and then when you subject B to another condition you get C. So you're supposed to identify A, B and C, etc. Yeah, so this kind of question is known as structural elucidation. They tend to be quite difficult with students, but you will only be good at it after you have perhaps satisfy 1, 2 and 3. Yeah, because you need to be very familiar with the reagents and conditions as well as the mechanism before the structural elucidation kind of question make perfect sense to you. Then, of course, the final category we are looking at will be the novel kind of question. Okay, normally I just classify it as others. They can be data-based, meaning we can give you some data, or we can give you some graph, and then you are going to make sense out of it and then try to decide what are the information that is important for you to solve the question. Yeah, so 5 can't really be studied. So you need to be very familiar, and you need to be very thorough in the way your thought processes flow. Yeah, so you need to have a very logical mindset in order for you to do a question related to the database kind of organic questions. Yeah, so that means fundamentally you need to be very familiar with the contents, and after you're familiar with them, I think the rest are just details, and you're going to get them quite easily. Okay, so without further ado, we'll jump into question 1. So you're supposed to synthesize 2-methylpropanoic acid. So we need to know how 2-methylpropanoic acid looks like. So it has a propanoic acid framework. So I have a OH here, carboxylic acid OH, and then at second position I have a methyl group. So this is 2-methylpropanoic acid. In case you don't know how is it named, 1, 2, 3. Number 1 is always the functional group. So the second position will be the CH, and then it's directly bonded to a methyl group. Yeah, so there are 4 carbons in total. Then you're supposed to synthesize it from propene. So if you look at propene has only 3 carbons. Yeah, so if I'm just going to look at propene itself with 3 carbons, I'm going to end up with a product with 4 carbons, right? That means that I need to add a carbon. And based on what you have studied for this particular topic, in order for you to add carbon, normally it is being introduced as a nucleophile. Yeah, so maybe ethanolic casein will have come to your mind. Because when you introduce the carbon as a nucleophile, the CN, you can easily hydrolyze it to give you the carboxylic acid. So that might be something that you can think about. Yeah, so you notice that when I think about it this way, right, I'm actually working backwards. Okay, so this idea of working backwards, right, is what we call retrosynthetic analysis. So this is a Nobel-winning work, which I have shared with some of you during tutorials. Retrosynthesis in short. Okay, so if I think of it backwards, right, then I'm going to end up with a precursor to the carboxylic acid as the cyano compound. So if I number the carbon, there will be 1, 2, 3, and then 4. Yeah, so carbon number 1 is the carbon that I've introduced, likely to be through nucleophilic substitution. So again, if I think backwards, okay, so the precursor to this particular halogen alkenes is likely to be a Br. Yeah, it's really up to you. You can choose Br, you can choose I, you can choose Cl. It's really up to you. Okay, and then I think you can easily go from the propene to this by simply introducing HBr gaseous. So this reaction is known as electrophilic addition. You should be able to draw the mechanism. So if you want to revise alkenes, then you will probably want to see whether you are able to draw the mechanism for this particular step. Okay, if not, then it is timely for you to revise alkenes. Then the next reaction will be nucleophilic substitution. Right, so this is a new reaction you have learned in this particular chapter. So you need to know the reagents and conditions as well. Usually we do it with KCN dissolved in ethanol, or we call it ethanolic KCN, and then we heat it. Yeah, so the cyanide will perform a nucleophilic attack on the carbon bonded to the Br. Yeah, so in this case, I'm going to get the cyanide in. And then, of course, the final step will be hydrolysis. So hydrolysis, because I'm going to get a carboxylic acid, so I will do acidic hydrolysis. H2SO4 equals, heat. Yeah, normally sulfuric acid will be the choice unless the sulfate can be precipitated out. Yeah, so if it cannot be precipitated out, sulfuric acid is usually the choice. Yeah, again, cheaper, easier to prepare, etc. So all this you don't need to worry. So for your case, in exam, you can use HCl if you wish. Doesn't really matter. Okay. Then with that, we can move on to part B. Yeah, part B, if you look at the whole setup, then I have 1 bromopropane. So this is 1 bromopropane. Okay, eventually I'm going to end up with 2 aminopropane. So now the second position has the NH2. Okay, so if I number the carbon, 1, 2, 3. So if I go by this way, right, it seems that I need to sort of create an electron deficient center at the second carbon rather than the first carbon. Because if I simply just subject 1 bromopropane to ethanolic ammonia heat in silk tube, right, I'm going to get 1 aminopropane. Yeah, so in that case, with that thought process, then I know that the precursor to this is likely to be the Br at the second carbon. Okay, so this is 3, 2, 1. So the condition will be obvious. Ethanolic ammonia heat in silk tube. Okay, so this is the standard condition that you have studied in your notes. So that should be something that you should be able to come up with. It shouldn't be too difficult. Yeah, and then how can I get the BR in the second position? Then you know that prior to halogen derivatives, you learn arenes, you learn alkenes. So maybe alkenes is the one that we are looking at. Anyway, 1b gives us a glimpse how we can get the BR into the second carbon. Yeah, so I think this shouldn't be that difficult. Yeah, so from here at least what I can do is I can simply subject it to HBr gaseous, okay, and then of course from 1 bromo I can easily perform an elimination using ethanolic KOH. Okay, ethanolic KOH heats. Yeah, so this will give me the elimination condition required to eliminate HBr. Yeah, so I think 1b is slightly easier than 1a. Yeah, so I hope that you in this particular review you get to learn a technique or a strategy to do synthesis question, that is to think backwards. And of course prior to thinking backwards, you need to ensure that your fundamentals is strong. You need to know your reactions. Okay, we'll move on to question 2. So question 2, we have an optically active sample of compound R. So that means that compound R has one enantiomeric form, but they did not tell you which form is it, so it doesn't really matter. Okay, it's heated under reflux with aqueous sodium hydroxide, and I get 2 organic products, P and Q. So I'm just going to write out P and Q. So P plus Q. So the molecular formula for P is C10H12O. Molecular formula for Q is C10H10. Okay, if I wish to, or maybe if you wish to, you can actually write out the molecular formula for R, but it's not necessary. Yeah, if you do a quick count, 6 carbon, 8, 9, 6, 7, 8, 9, 10. So R is C10. 5 H here. Okay, then 7, 8, 9, 10, 11, 12. Okay, so 5, 6, 7, 8, 9, 10, 11, H11. Okay, BR. Okay, then if you look closely at the molecular formula, you notice that the BR is being replaced, and then based on the formula for P, right, there seems to be an extra OH. So you can see that there's an O, and then the H actually increased by 1. Yeah, so from here it is pretty obvious, if it's not so obvious to you, that P will be a nucleophilic substitution product. So this is a nucleophilic substitution product. Okay, so what is the nucleophile? So nucleophile will be OH minus, likely to be, because if you just compare the formula, it seems that the BR is being replaced by OH. Okay, then what about Q? Q has a formula C10H10 over here. Yeah, so you notice that if you compare these two formula, just look at the end part. You notice that a HBr is gone, so it's like a minus HBr. Okay, from R to Q. So this is likely to be an elimination product. So this is an elimination products. Yeah, so if it's an elimination product, what kind of elimination are we looking at? So we are looking at elimination of HBr, likely to be conjugated as well, and it needs a beta hydrogen. So if you do a quick check, you need to have a beta carbon, or in particular sp3 hybridized carbon that contains a beta hydrogen. So beta hydrogen is likely to be here. So if it's here, then I can easily get Q. Yeah, so Q will likely to be having a phenyl ring with alkene here, as well as another alkene here. Okay, so maybe I didn't draw it very clearly, but it should look something like this, and like this. Okay, so it's a conjugated alkene conjugated with the phenyl ring. So that should be Q. What about P? Yeah, P is a nucleophilic substitution product. So you were told that it is not able to rotate plane polarized light. So was neither of the sample was able to rotate plane polarized light. So that means that either I get a compound without a chiral center, or I get an enantiomeric mixture. And you can see that this is actually a tertiary bromide. Yeah, so it's likely to undergo SN1. And it does make sense, because if you look at the potential carbocation that can be formed, Okay, I'm just going to sketch out over here. So this is the carbon, and then I'm going to have a CH3 here, and then a group projecting out with an alkene, right? This particular carbocation is trigonal planar and it's tertiary, and most importantly, conjugated with the pi electron clouds in the phenol ring. Okay, so if I'm just going to remove this ring here, I'm just going to draw in the unhybridized p orbital in the benzene ring. You notice that this is a delocalized electron cloud, and over at this carbon there is an empty p orbital. So this is empty. So this empty p orbital is going to overlap side on, and the delocalization is going to help stabilize the positively charged center. Yeah, so those of you who have heard me from earlier lectures, you know that this carbon is known as the benzylic carbon. So the benzylic carbon is highly stabilized. Okay, and because it goes through a carbocation, you can also explain why neither sample of P is able to rotate plane polarized light, because the hydroxide, okay, anion approaches it from the top, okay, and bottom plane with near equal probability. So I'm going to end up with a racemic mixture. Okay, so with that idea, I should be able to confirm the structure of P to be like this, and it's a racemic mixture. Okay, so the type of reaction that P and Q undergoes from R, I think I've highlighted earlier on. Nucleophilic substitution to get P, the nucleophile is OH minus, and for Q, to get Q is elimination. Yeah, so eliminating HBr. Then account for the observation in the optical activities of the samples P and Q stated above. You should illustrate with diagrams where appropriate. So this is the diagram that I'm going to illustrate. I know I illustrated here, but I'm going to illustrate using this diagram with the hydroxide approaching from the top and bottom plane with near equal probability, and I'm going to draw up a racemic mixture. So in the presentation of my answers, I will definitely showcase this particular projection. Yeah, the reason why I need to showcase this is because it is a requirement to illustrate my answer, so that the examiner knows very clearly that I understand what is going on, or the students understand what's going on. Because if you do not illustrate your answer clearly, then you do not want the examiner to second guess whether you are just guessing or you could randomly just come up with an answer without understanding the reasonings. Yeah, so I think this will allow me to clear with the examiner that I understood why P cannot rotate plane polarized lights, and why Q can't rotate plane polarized lights, because there's no chiral center. Yeah, okay, so the mirror image end itself is superimposable, so therefore Q does not have optical activity. If you still remember how Q looks like, Q looks like this, okay, like this. Okay, so if you try to draw the mirror image and itself are superimposable. So it's not able, it does not have an asymmetric electron cloud, so it will not be able to rotate plane polarized lights. Okay, so that's the answers you need for part C. And then earlier on I mentioned one of the highlights of organic chemistry in questioning is you get different types of questions. So the last question 1D, right? 2D, it's on distinguishing test. Okay, so normally it will be PARC at the end. So they ask you describe a chemical test with appropriate observations. Which would confirm the identity of R as bromoalkene. So there are a lot of ways you can do that. You can use ethanolic silver nitrate if you wish to. Ethanolic silver nitrate. Silver nitrate. Yeah, this will be the easiest, because once you put in ethanolic silver nitrate, cream PBT or silver bromide will precipitate out. So that will allow you to confirm that R is a bromoalkene. Yeah. If you want to further confirm, you can add excess concentrated ammonia, and then you would expect the cream PBT to dissolve. Yeah. Another way for you to describe the test would be a slightly more long-winded way. So I think number one is you need to put a sample in sodium hydroxide, okay, and then you warm it in a water bath. So sodium hydroxide, and then you warm in a water bath. And then after that you add excess nitric acid The excess nitric acid is to neutralize the OH minus, yeah, so that the excess OH minus will not precipitate out silver hydroxide when I add silver nitrate in. So excess nitric acid. Usually you test for excess nitric acid by simply dipping a blue litmus in, and then you check whether the blue litmus turns red. Okay, then after that you can add silver nitrate. This is not ethanolic silver nitrate, just silver nitrate aqueous. Okay, and then after you have added in silver nitrate aqueous, you're going to expect a cream PPT of silver bromide. Yeah, then after the cream PPT of silver bromide appears, then you can check for its identity by adding corn ammonia to check for this is to check whether AgBr dissolves. Yeah, because you can't really confirm that it's silver bromide. Sometimes when you do not have the white PPT and the yellow PPT side by side for comparison, you might not be able to tell that it's cream. Yeah, if you're not so sharp, especially most of us are not so experienced because we don't look at them every day. Yeah, so I think putting in the fourth point, concentrated ammonia, to see whether the PPT dissolved, I think it's a very helpful point to ensure that you know what's going on. Okay, so that's the end of our review for class exercise 2. Hope you find it useful. Do look out for further review next time.